Welcome back again. So for topic C2, we're still going to be working with volume, but instead of just prisms and cylinders, we're going to add a few new shapes. We're going to add in pyramids and cones, which are basically round pyramids, and then also spheres and I guess hemispheres as well. So we'll look at those, and then that will take care of it for this set of stuff. But just like we did with prisms and cylinders, let's define these things first. So a pyramid, and we'll see in just a minute that a cone is pretty much like a pyramid in the same way a cylinder was pretty much like a prism. But first, let's define a pyramid. So instead of having two congruent parallel bases, like a prism does, a pyramid has just one base. So this still needs to be a 3D shape. But it only has one base, but then of course it needs a little bit more than that. It has one base. It needs to have flat faces or flat sides and straight edges. And we need to make sure, we'll see this in the picture, that everything from that base connects to just a single point, which we call the apex of the pyramid. So we'll see that in these pictures below. So this first one is what you probably think of when you think of a pyramid. It looks like maybe an Egyptian pyramid here, but this has a base which happens to be at the bottom. That doesn't have to be true. The reason I chose that as the base is because then there's this other point across from the base, and that point's the apex, because from the base, every corner of the base connects up to that single point up here. Because the base is a rectangle, this would be called a rectangular pyramid. The pyramids in Egypt are square pyramids, more specifically. And then the second picture is also a pyramid because it has a base and then everything connects to an apex. But I have a few different options for this one. So maybe I choose this triangle as the base, and let's see if that works. If I connect from this corner and that corner and that corner of the base, all of those connect up to the same point. So sure enough, that works, and this is a triangular prism. But what I could also do, there's no rule that says I have to choose the bottom to be the base. So maybe I choose this side back here as the base. Let's see if that works. That's a triangle, and the three vertices of that triangle all connect. Yikes. Connect, I said, out to this point out here. And so that's a different way to see that this is a triangular pyramid. And then, as I said, just like a cylinder is basically a prism, a cone, as you see here, is basically a pyramid. A cone is going to be, I'll put it in quotation marks, because pyramids aren't supposed to have rounded edges or rounded sides. But a cone is basically a pyramid. It's just that it has a circular base. So here, got a circle. And so every point, there aren't any corners, of course, but every single point around the edge of that circle connects up to that same apex. That's some good drawing there, Miss Kennedy. Well done. But we can still treat it the same way that we do a pyramid. So then finding the volume of a pyramid or a cone. When we did it with prisms, I'm actually going to start there. So for a prism, volume is capital B times H, right? That's for a prism, and then it also worked for cylinders as well. We're going to change this up in just a minute, but let's remind ourselves of what we already know. The capital B was the area of a base. And then h was the height of the prism. Now it's going to be the height of our pyramid. And we're going to make one change to our formula, which is to put a 1/3 in front. Since everything is going up, like on this rectangular prism, everything's going up to a point rather than going up to another rectangle, that's going to cut down on the amount of space you can fit inside that shape. So specifically, it cuts it into thirds, and we just get a third of the volume. So as we did with prisms and cylinders, we're going to do basically the same thing here and treat it as a two-step process. First, we're going to find the area of the base. And then instead of just multiplying that by the height, we're going to multiply by 1/3 and the height. And I'll put that in quotation marks to remind us kind of to be careful when we use the word height. We'll see that in the examples below and right here. Just like with everything, when we did area of triangles, this was true. Now that we're dealing with volume of pyramids, it's still true. The height that we're dealing with has to be perpendicular to the base. So on my pictures above, I'm going to go from the apex and I'm going to go straight down to the base and make a right angle. In other words, I'm not going to travel along the slanted edges. I'm going to go straight down, make a right angle, and you can see a kind of letter H getting formed in there. Over here, I chose kind of a weird base and a weird apex. We'll see if I can draw this. But from the apex, I'm going to go straight back, yikes, and try to imagine, it's drawn terribly, a right angle with that green triangle. For this cone over here from the apex, I'm going to go straight down, make a right angle with that circular base. So then just like we did before with the prisms and cylinders, we have just some examples. The program that I use to draw these pictures will shade certain things just to make it look three-dimensional. Sometimes the things that it shades will be the base, but not always. The shading is just there to make it look three-dimensional. That may or may not be the base. So let's see if this yellow thing actually works as our base. From each vertex down there, we do go straight up. All 4 of those vertices connect to a single point. So that yellow rectangle is a good choice for the base, and then this red point up here is our apex. So we'll think of it in 2 steps. First, let's focus on, let me make that green. Let's focus on this green rectangle and ignore the rest of the shape for now. That rectangle is 32 feet across, 17 feet the other direction, and we have right angles because we have rectangles there. So the area, just little b times h, 32 times 17, which is 544. So in order to find volume, we started off by finding an area. Now we're ready to take it to step 2 to find the volume. So I'm going to take the 544, but then I'm going to do 2 other things. Since this is a pyramid that goes to an apex, that means a 1/3 has to show up just automatically. The other thing that needs to happen is the distance from that apex straight down, or sort of. So bad at drawing on this, guys. I'm sorry. Straight down, making a right angle down here. So the height of this pyramid is 24 feet. So 544 times 1/3 times 24 gives me 4,352. And everything up here was measured in feet, but since I'm measuring volume, it's going to be in cubic feet because it's a 3-dimensional measure. So 4,352 cubic feet. Really, the only difference with this versus what we did with prisms is simply that 1/3. Everything else stays the same. So with that, may not need as much help for these others because they're so similar to what we've already done. So here again, pause the video and try the next 2 examples on your own. And then when you're ready, then unpause. So here are the answers for those 2 with my steps shown. In each case, you can see I highlighted the base in green, and I found the area of the base, depending on what shape it was. Here it was a triangle, and then we had a circle. And then once I knew the area of the base, I multiplied it by 1/3, because we were dealing with a pyramid. Everything goes up to an apex. Over here, a cone is basically just a pyramid. Everything goes up to an apex. So I multiplied by 1/3, and then just the distance between the apex and the base, and then rounded to 2 decimal places, and went with cubic units because I was measuring volume. You can pause the video if you want to look through those steps a little bit. And as we did with prisms, let's take a look at some working backwards problems, and then we'll look at spheres. So a certain pyramid has a square base with side lengths of 9 meters. The pyramid's volume is 135 cubic meters, and they want to know the height of the pyramid. We did a very similar problem in the notes for prisms as well, and we changed it up just a smidge since this is a pyramid instead, but it's still this 2-step process. Focusing just on the base, they told me, highlighted in green, it's a square base. I'm extra bad at this today. A square base with side lengths of 9 meters. Ignoring everything else, I know the area of that square is going to be 9 times 9, so 81 for the area of the base. Then we start thinking about volume. So I know I've got 81. Then they told me it's a pyramid, so that makes a 1/3 show up in my formula, times the height of the pyramid, or the distance to get to the apex. The trouble is they didn't tell me that, so I'm going to leave that as an H. I'm going to use this other piece of information they gave me, that the end result, the volume, is 135. So we can deal with that in a few different ways. However you want to solve it is fine. But typically just kind of dealing with those fractions, people like to get rid of fractions first. So I'm going to multiply both sides by 3. 3 times 1/3 is 1, so those have canceled out. I have 81 times the height we don't know. Gives me 405. Then I can divide both sides by 81, and I get h equals 5. There are other ways that I could have done those steps to solve it, but if you got to h equals 5, then all is well. And let's think about units as well, since this is a height. So I have some stuff in cubic meters, so my choices are meters, square meters, cubic meters, or perhaps, as we saw last week, maybe degrees. Since this is height, and I would just measure it with a ruler, not covering it in tiles, not trying to fill it up with cubes, the height is 5 meters for that pyramid. The other example looks super similar to one we did with prisms and cylinders, but this time, instead of being a cylindrical tank, it is conical, which just means it's cone-shaped. So a conical tank has a volume of 50 cubic feet and a height of 6 feet. To the nearest 1/10 of a foot, what is the radius of the tank's circular top? Pause the video and give that one a try on your own, and then unpause when you're ready. Okay, so final answer here was 2.8. The instruction said 1/10 of a foot. If you had gone to 2 decimal places, I would forgive you. But here we focused on the base first. The trouble was that we didn't have a number to plug in for r, but that's okay. I just left that as pi r squared. The fact that we were dealing with a cone told me to put in a 1/3, and the height of 6 feet told me to put a 6 right there. And then as with the other, there are a ton of different ways you could have solved this. I did it probably in more steps than I needed to. But I multiplied by 3 to get that 1/3 to go away. And that gave me a 150 over here. Then I divided by 6 to get the 6 to go away. That gave me a 25 over here. I divided by pi to get the pi to go away, and I had to round that to 7.96. And then finally, I got rid of the squaring by taking a square root on both sides. And so that does it for cones, but we still have just one shape left. It's kind of the strangest formula, but it's also the most difficult for us to make difficult for you. There's a formula and that's it. There's not much we can change for a sphere. The volume of a sphere. Because it's round, pi gets involved, just like circumference of a circle, area of a circle, and now volume of a sphere. We've got a pi involved. The radius plays a part. Because we are 3-dimensional, we're going to cube it. Like when we did area, it was pi r squared, but that was flat. Now we go with something cubed, but we're not quite finished yet. The other part of this coefficient in front is a 4/3. The reasoning behind that, if you wanted to take some calculus, I could show you why that 4/3 is what it is. But for right now, if you'll just trust me, that would be great. But the nice thing about this is once you know the radius, that's it. I don't need the area of the base. I don't need an apex. I don't need I don't need anything fancy. I just need the radius and a formula. So for these examples, this is about as tough as we can make them for spheres, and you'll see they're not very tough. The volume of this sphere. Well, it's a sphere, so I'll use my volume formula, 4/3 pi r cubed. That's what we have here. And this time they gave me the radius, so 4/3 times pi, and then our radius is 6 meters. On your calculator, to get that cubed button, there are a few different ways to do it. You could just do 6 times 6 times 6 if you're in a pinch. Or you might see a button that looks like a little housetop to get that exponent to happen. That may actually be what you use for squaring as well. You might see something that looks like x to the y. Some of your calculators might just have box raised to the box. But again, in a pinch, just remember 6 cubed means 3 6s multiplied together. But I can just type this in to my calculator exactly as it appears, 4/3 times pi times 6 cubed. And I get 288 pi, if it gave you the exact answer. But they told me 2 decimal places. So use your toggle button if you need to. And I get 904.78. And since we're dealing with volume, our answer, the volume would be in cubic meters. So that's just a direct application of the formula, plugging in the radius because they told it to us, and then typing into a calculator, just with some new tricks for how to do that. And then I went crazy, and I went with a hemisphere. Oh no. Again, that's about as bad as it can get. A hemisphere is simply half of a sphere. So one way to deal with this is just to imagine, to start with, that it's the whole sphere, and then we'll cut our answer in half. I know, it's super crazy. So if we had the full sphere, 4/3 pi r cubed, radius is 8 inches. So 8 cubed times 4/3, depending on your calculator, your answer may look a little different from mine. but on the blue and white calculators that most of you have, it probably gave you this. If it gave you the decimal version, that's okay. 2,144.66. But that's for the whole sphere. And I only want half of that. That's what a hemisphere is. It's like a semicircle and a hemisphere. So I'm going to take the answer I just got. I don't even have to type anything into my calculator to get that number. It's already right there. And I'm going to divide it by 2. And I'm going to get 1,072.33, and this is a volume, so it would be in cubic units. So there, like, again, it's pretty tough for us to make these problems any more difficult than that for spheres and hemispheres. We use the sphere formula and then split it in half. There are other ways to get to that answer. Of course, those other ways are fine as well. And then here I didn't give you a picture, and whoa, I gave you the diameter instead of the radius, but I think you can handle it. Pause the video, give it a shot, and then unpause. And here's your final answer for this one. We just had to split the diameter in half to figure out the radius. It was a formula, 4/3 times pi times 5 cubed. And then just a rounding reminder, the instructions said 2 decimal places. My second decimal place was a 9. The guy afterwards told me to bump that up, which is weird. So instead of changing a 9 into a 10, I changed a 59 into a 60. But there again, with spheres, nothing too crazy can happen. Maybe I give you diameter instead of radius. Oh no. Maybe I ask for a hemisphere instead of a sphere. Oh no. That's about the worst we can do. Asking you to find a missing radius, like I give you the volume and ask you to find the radius, that involves a little bit of math that you haven't learned yet, so we won't ask you to do that. That's something that you would be able to do in like an Algebra 2 class. So that does it for week 2. You have 2 homework assignments, C1. Oh, this is week 3. Oh, heavens. So that does it for week 3. Assignment set C, with your 2 homework assignments, C.1 and C.2. And then you get spring break. And then after we come back, we'll spend some time reviewing. And then Tuesday, April 21st, which feels like it's 50 years away, that is when your Unit 9 test is going to be. But during spring break, use that time to get caught up if you need to. We aren't going to give you any new work. So get assignment set C taken care of, and if you're on track with sets A, B, and C, then you won't have any new math to do the week of April 6th. See you next time.